So we are back with Pset 3 solution videos. So let's look at our first problem. So we have a yellow material that's rubber elastic above TG, so we can use our rubber elasticity, basically formalism. So let's see, we are given that the black walls are rigid and immovable and suspended in space. The material is not bound to they're frictionless. The Young's modulus is 1 GPa, and we have our expression for a rubber elastic material in terms of what the Young's modulus is going to be equal to, so our density, and that's going to be 1 GPa times our Avogadro's number times our molecular mass between our crosslinks. I don't know the initial dimension in the one direction, but the stress in the one direction is going to be 500 megapascals, and the force per polymer / crosslink train is going to be 5 times 10 minus 21 newtons. So sigma 1 is 500 times 10 to the 6th. F sub 1 is going to be equal to, and again, that is the force per polymer. So again, that's a very critical kind of distinction there. So the force per polymer is going to be that value per crosslink chain. All right, and we could get our V naught is equal to 0.184 times 10, and then actually it's not 10 to the 3, it's just meters cubed, so ignore that one. So in this scenario, we must conserve volume, so alpha 1 times alpha 2 times alpha 3 must be equal to 1. As I pull in that one direction, the length of the one direction will increase, and our L naught in the one direction is given there, or we'll figure out. Alpha 2, as I pull there, that will also basically shrink, as will alpha 3, and that will be equal to 1 over the square root of alpha 1. So this is very similar, actually exactly similar to our old scenario. Because the walls are not attached, that is just going to be square root of alpha 1 to our uniaxial rubber elasticity kind of problem that we worked with previously. We know L naught 2, V naught must be equal to L naught 1 times L naught 2 times L naught 3. So even though we don't know that initial L naught direction, because we have V naught, we can solve and actually start to solve for some of these problems. So let's go ahead and continue. And now we can actually, the problem is pretty well sketched out at this point. We also know that our F sub 1 is equal to minus T times the derivative of delta S1 over DL1, and a constant temperature and pressure. So we should remember, always keep that in mind. What is the temperature of the system? What are our extension ratios? What are our forces in one direction? Et cetera, et cetera, et cetera. So we should be able to kind of go through and try to solve the rest of those values. And then thermodynamic variables, number of crosslinks. We know essentially what solve for all the unknowns given the initial information. And then we could kind of look at some different tweaks on the problem per se. So again, we want to list out, be very formulaic in terms of how you, or systematic, excuse me, instead of formulaic, be very systematic at how you want to approach this problem. Sketch it out as we've kind of done here. We could actually basically expand upon this a little bit more, but this is essentially how we are going to go about solving this problem. We also have our other expression for Young's modulus that we can probably find that to be a little bit more useful, but we could probably come to that once we actually start going into our Mathematica notebook and starting to solve some of the problem a little bit more quantitatively. We should also know that we have our equation for stress in one direction is just going to be Z times F sub 1 over A naught, and we actually already know that F1 value. Excellent. Our A naught is just going to be simply times the L naught 2 times the L naught 3, so that cross-sectional area. So that's what we're going to use for our sigma. Let's zoom out a little bit more here. But now we can now start to, I think we've done enough work, at least sketching it out wise. Now let's get into Mathematica. Let's try to get a little bit more quantitative, because at this point we can't just leave it here. We actually now need to do the math. But again, this is a good way to start your problem. Always keep kind of these equations in mind, and then now we can work with them. Again, clear everything. Separate notebooks for different problems is a good idea, but again, it's just how you want to work with your, essentially with the problem, with the constraints of the problem that you're given. So let's go ahead and now we can start typing. And some of this can be done ahead of time. So alpha 1, L1 over L naught 1. We know that alpha 2 is going to be equal to alpha 3, which is going to be equal to 1 over alpha 1, or square root of alpha 1, excuse me. So that's equal, alpha 3 is equal to alpha 2, or square root of alpha 1 as well. Excellent. So we can now start to define the rest of our problem. So always starting out with the alphas is a good idea. Define, looking at the system constraints, what's moving, what's not moving. We can define our change in our entropy. So minus k over 2, let's keep that in parentheses, minus k over 2 times basically alpha 1 squared plus alpha 2 squared plus alpha 3 squared minus 3. And then we have our del S. I'm keeping it very general. You can define k at this point, or you can kind of just define it later on. It's completely up to you. Although make sure you redefine essentially your systems. My f sub 1 is going to be minus t times the derivative of del S1 with respect to L1, the dimension we're pulling. So we've got our f sub 1. We already know that that's going to be equal to our 5 times 10 to the minus 21 newtons. But again, at this point, there's just a lot of basically undefined variables, but we can keep that in the back pocket. You can actually define the equation right now if you wanted to, but that's just another way to solve the problem. So there's a lot of ways that you can solve many of these problems. We also know that our volume is 0.184. So actually we can solve right now once we define L naught 2, L naught, yeah, exactly. Finally got rid of that 10 to the 3. So I can define L naught 2, and then we can just write that down. Let's zoom in a little bit here. So L naught in the 2 direction is just going to be that 85.6 centimeters. So L naught 2 is equal to 85.6 times 10 to the minus 2. My L naught 3 is going to be equal to 215 times 10 to the minus 3. And with that, we can solve right now for L naught 1 as well. So this double equal L naught 1, L naught 2 times L naught 3 times L naught 1. Solve for L naught 1. And we have L naught 1. Excellent. And as we can see here, L naught 1, it is going to be, actually, we'll figure that out initially. So that's my L naught 1. And let's see where else now. So we've got L naught 1. That's a good start. We can kind of reevaluate possibly. We're starting to kind of cancel out all of the unknowns in our system. And kind of essentially see what our equations are telling us at this point. So we've essentially utilized that V naught equation to solve for one of our initial lengths, and then now we can start to plug in for some of these values and start to solve for some of our unknowns in our problem statement. We are not given temperature as well. Or I could just leave it, again, I could leave it undefined if I just want to kind of keep it general, but I've got that value there ready for when I need to, or ready for when I want to use this. All right, so our force equation. Our force equation will simply be 5 times 10 to the minus 21. And then we'll set that double equal to basically F1. So that is our force equation. So we know that that is the force per polymer. So per polymer / crosslink, chain. So those are just going to be that value, newtons per crosslink chain. So that is our force equation there. Our stress equation is 500 megapascals, 500 times 10 to the minus 6, times Z times F1, or F1, divided by our A naught, which again is just going to be L naught 2 times L naught 3. So we have our force equation, we have our stress equation. Excellent. We already utilized our V naught, or you can use that to solve that simultaneously as well, but that one is simple enough where you can just pull out that value. So we're working towards essentially our solution. We also know our Young's modulus equation. So that will be another useful one that we can start to play around with and start to define. But again, as we go through this, we want to be able to kind of, and actually we can rearrange that right now. So we defined previously our Young's modulus expression. But there is often an easier one that you may encounter. So the molecular mass is one, or the mass per crosslink, is actually something that's you can measure that experimentally. But when you're solving some of these problems, we want to kind of know the relationship, or how did we actually get to our m sub x. And really, we want to know that the number of crosslinks per volume is simply going to be Z, the total number of our crosslinks, polymer chains, etc., divided by my volume. And my volume is just going to be the initial volume of material, R V sub naught. So we have another relationship here, N sub x is equal to Z over V naught, that we can use as well to plug in essentially into our system. So we can use this expression and we can plug that in into our Young's modulus expression as well. So E is going to be equal to, once we make that switch, and we can kind of see here, just doing the mental math in my head right now. So we can change this. So we can actually rewrite our expression for Young's modulus as N sub x, the number of crosslinks per unit volume, times our Boltzmann constant times temperature. So with this, we can actually simplify our equation. We get another set of equations. So we know our Young's EQ is going to be equal to 1 times 10 to the 9th gigapascals equals, and then now we can just do simply Z, or actually, excuse me, Z over V naught, or N sub x if we want to define that expression. N sub Z divided by V naught, or Z divided by V naught, times K, Boltzmann's constant, times T, and then voila. So we've got another equation that we can solve for. So now we can kind of start to take a peek now and look at our unknowns. So we already solved, we figured out, previously we could define what L naught was. So let's look at what our equations, what we're left with. So V naught, let's just define that explicitly here so that we can give in, let's define K, 1.38 times 10 to the minus 23 joules per Kelvin. We want joules because we're working with stresses, all those good things. So Young's equation, now just temperature, Z is our variable, and L1. So L1, T, Z. 3 equations, 3 unknowns. Let's solve this bad boy. So you could just go and solve these problems, very, again, systematically in this way. So I'm going to solve my force equation, my stress equation, and my Young equation all at the same time. I could specify, or we'll spit out the answers, but I want L1T here. We can look at some of the solutions. I know I can't have negative lengths, so I need to kind of pick the real values. So here I can see my L1 is growing, makes sense because I'm pulling in that direction. Temperature, and then my Z. So there we go. So do I know what the temperature? Yes. So I'm going to define that, and I have all these kind of unknown parameters. Once I define everything in my system, everything else will come. So for example, I could do, if I type it correctly, alpha 1 greater than 0, alpha 2, alpha 3. They should be the same. Makes sense based on our system. We know what our temperature is. We can define that, and now we can look at all those other parameters that what we're asked to solve for. So at this point in the game, it's just all calculation at this point. So what we can do is I can solve for alpha 2 as well. So alpha 2, I know that value. I know L naught 2 divided by L naught 2, and I can find L2. So if I just want to find those lengths as well. So there's my L2. There we go. I could do the same thing for alpha 3. Find L, the final distance, final length, excuse me. I could find L3 here, set it equal. L2, L3, we've got it. In case I were to ever ask for the strain, maybe that might be a problem. Actually, I do ask for the strain here. So we could do the strain in one direction. You could do the strain in all the other directions as well, just to make sure that makes sense. So we got that, divided by L2. L3 should be the same because we have the same extension ratio, but let's just double check it to make sure that we're okay. Fantastic, because when I pull, it should contract there. And now we can get to our other nittier-grittier questions. I could solve for my N sub x as well, number of crosslinks. So N sub x is equal to Z, so I could define Z. Z divided by the volume. Z divided by V, or Z divided by V. Or it should be Z divided by V here. That's a little bit of a mistake, so make sure we're not doing that. So N sub x is number of crosslinks per unit volume. So that needs to be Z divided by V naught. I'll make that correction in a subsequent video. But so Z times F1, so we can have that. That's basically going to be your total force. So Z, what is your actual force in the direction times the number of those polymer chains. So we'll make sure, again, note that what thermodynamic variable contributed, entropy, neglected, enthalpy of fusion. We're also asked essentially, and we got our how's it going to change the function of temperature, our Young's modulus. And we know essentially those different variables and how they may change basically in here. So that is, again, the whole elasticity comes from a entropic spring-like restoring force. So make sure that you are able to suss that one out. Found the number of crosslinks. Again, make sure to divide that by V naught instead of times V naught. So make sure we get that one a little bit correct next time. Excellent. So before we move on to the next problem, now instead of pulling in the one direction, I push. What are my extension ratios? Well, if I push, and again, it doesn't work for compression, but if I were to push, my alpha 2 is equal to alpha 3 again, but now this time as I push in one direction, those must be equal to 1 because the lengths are not changing, they're constrained. So if it was pulled and bound to one of the so let's get into the next problem. So I'm working with a novel material in the stress state, purple. Mystery material is in a cube, the black outline. So rigid on all sides, denoted by the dashed cubes and the 1-3 planes. Material is bound to the cube on the 2-3 faces, so those dashed kind of blocks that you see. But the material is not bound basically on the 2-3 faces. So on the 1-3, I am basically stuck. On the other ones, I am not. Assume no friction, so we're bound here. The material has a thermal expansion coefficient value. Temperatures decrease to minus 150. We are given strain measurements and we're given applied forces. So we need to write out all the stress strain tensors and do lots of good and fun things essentially in this problem. Cube has initial length of 5 inches. So side length. So we don't know what our material is. We have our coordinate system. Let's figure out where strains will exist and where they're not going to exist. So clearly there's a stress in the 3-3 direction. We can see that there. What about a stress in the 2-2? Yes, because the material, it's going to want to contract and it's being pulled up, but it's being constrained by the walls. As I pull up and as the material contracts, there will be no stress holding it on the 1-1 direction effectively. There will be strain in 1-1, no stress in the 0, in the 2-2, or no strain, excuse me, in the 2-2, and then there will be strain in the 3-3. So we know the strain in the 1-1. We know the strain in, basically, we know the strain in the 3-3. We know the strain in the 1-1. So now we can start to solve this problem. And hopefully we can figure out the stress in the 3-3. So let's define our thermal strain. So we have our alpha, 10 minus 7. That's not going to help us in determining what the material is. We have our del T, final temperature of a minus 150, minus our 25. We don't have to convert to Kelvin here because, again, you're just adding on the 273 to both sides anyway, so you don't have to deal with that. If you want to, good for you. It's always better to be safe than sorry. So we have our del T, so we could tack on now that thermal strain problem that we usually have. So we got it, minus 150, minus 125. Again, we can even just do this for fun if we want. Just show you get the same value. But again, it's just an exercise in math. But we do it. I do it anyways because, again, I want to make sure everyone feels good. And we have our del T. So I can define my thermal strain, epsilon T, alpha, or del T times alpha. It's not just del T, it's alpha times del T. So we got that. Excellent. So we have our thermal strain. It's compressive, as we would expect from our material. Excellent. So now what can we start to do? Well, I'm given my strain in the 1-1, or actually I could develop my strain 1-1 equation. But let me define it. So E11 is going to be equal to 3325. Actually, E11 is minus 217.5 times 10 minus 6. E33 is going to be equal, makes sense because we're pulling, 3325 times 10 minus 6. microstrain, so make sure that we're using that appropriately. Excellent. We can also define our E22 is equal to 0 here, but we can now start to write our strain equation. So our strain of the 1 over y times sig11 minus nu times sig22. So again, we could define sig11 as 0. So sig11 minus nu times sig22 plus sig33. We may know what sig33 is, and we see I've already made a big mistake here. And exactly, tack on that thermal strain. Be sure to do that. E22, we know that's going to be equal to 0. We can define that right here. E22 is equal to 0. I can move that over again, moving back and forth, making everyone dizzy. Set equal to, now we could copy that expression, or we could write it out. So sig22 minus nu times sig11 plus sig33. Struggling with parentheses here. Close it, plus ET. And then copy and paste. So I could do strain 333, 3 equations, and let's figure out our unknowns here. So I don't know what my material is. So I don't know y and I don't know nu. And hopefully if I find those, then I can figure out what the material actually is. So let's figure out what this problem we can do. We do know sig33 because we're given force is 8 times 10 to the 6 newtons. Divide out by that initial area, which is 5 inches. Always handy to use this 5 times 0.0254 inches to meters. Square that. So I have my sig33. Let's reevaluate. So now my unknowns are just sig22, nu, and y. So let's solve strain 1, strain 2, if I can spell correctly, strain 3. And I could ask it for sig22, y, nu. And let's see what we have. So something that's around 121 gigapascals, a nu of 0.3-ish, metal. Yay, we did it. And then we have our sig22 value as well. So we've got our full stress and strain tensors. We know what material it is, probably metal. At what temperature would the strain in the 3-3 direction be 0? That's a good question. I like it. Proud of myself for asking. So let's look at our strain 3-3 equation. And we can start to plug in some values that we know. So if I set nu is equal to here, if I set my y is equal to this, if I set my sig22 is equal to that, set our sig22, although we solve sig22 knowing about something about our alpha, but let's just say we had this applied stress state, or actually, and we were actually changing temperature to change this. So it's a little bit of a derivative. So let's clear T, actually, let's clear del T. Let's do sub-question. No, it's still inequality, so we need to get rid of del T. So let's clear del T. And let's reevaluate this. Still there. I need to reevaluate E sub T. So let's go up here. So let's reevaluate. Yep, let's reevaluate ET. All right. So now we could go back, get our sub-question equation. Now we can solve when is our set it equal to 0. Solve what is that del T. So that del T expression must be minus 3,500. So that's quite cold. So we could actually solve it. So for example, equals TF minus 298. That's our starting, temperature. Minus 3,000. So that's not going to cut it. But anyways, it's just a fun problem to show you how we would have to solve that out. So write out the full 3D principal and maximum shear stress tensors, i.e. the full 3x3. So we are in the principal stress state. So we are there. So right now, that is the principal stress state that we are in. So we don't have to do anything because we only have normal stress values. And then we know that we could actually get to maximum shear by a rotation. So let's go ahead and see. Let's quit our kernel quickly. because what we want to do, if we're going to start to do rotations, we want to go through and actually look up, actually have some of these notebooks handy. So these are all on our Canvas site, so hopefully many of you should be very familiar with them. So we can kind of pull these out and then see which functions are going to be useful for the particular problem that we're looking for. So I'm just going to kind of cherry pick here. And I'm going to paste in some things that I think may be useful. When we start to go through solving some of these and using some of these functions, it's going to be very important that we kind of keep our wits about us. We need to be sure about what we're rotating into, what we're rotating out of, and again, are our answers making some type of intuitive sense? So we can actually go ahead and start to solve some of these, but let's define our 3x3 tensor explicitly, actually. So even though I've cleared my kernel, I could actually still basically recreate that stress tensor here. So I'm just going to Shift-Enter, evaluate a lot of these functions, define my stresses, they're still here, and I can now start to go ahead and go through my stress tensor. So my stress tensor is just going to be my sigma 1. I am in my principal stress state, so there's only normal stresses. There are no shear stress values. So I've already got that one, sig 3, and I've got it. I know that if I'm in my principal stress state, I'm only going to have to rotate basically 45 degrees around any axis to get into my maximum shear stress state. So if I'm looking at the 1-3 plane, the 1-3 plane, the 1-2 plane, the 2-3 plane, it is not trivial to figure out a rotation, a full 3D rotation that actually maximizes all of shear. So I'm just going to show you if I rotate it around the 3 axis, an angle of 45 degree, make sure we type degree, then I could see some of my shear stress values. And if you broke this down and did more circle, you would realize that that would just be essentially the radius of your circle. And we could actually see that in the 1-3 plane, it would just be half of our, basically half of our sigma 3, and that is actually indeed the case, because we're doing 1-3 here, no sigma 2, and you can see sigma 2 is actually unchanged here. So you can do a similar exercise around the 1 axis, around the 2 axis, 3 axis. So you can copy this code, and you'll see the values are just slightly different. But again, it's always going to be this 45 degree angle, and you see that we're kind of maximizing those stress values there. So we can actually look at it here. If we rotate it that way, and you can see if we rotated it. So remember, it's always the transpose of a rotation matrix times the 3x3 or dotted dot the rotation matrix again. So that's going to be how we find our new stress state. And we've talked about that and done that several times in class, so hopefully it's a little bit familiar with you. Okay, actually it turns out the walls were not entirely frictionless. So we can actually see here. Let's go ahead, scroll down, we can kind of see, you can actually figure out the angle too. So let's look at our matrix form. And again, just kind of the similar things that we were talking about previously, to find that sigma, basically by a half. Again, we're just drawing our Moore circles effectively in these problems to solve those out. So if you divide that by 2, 2.48, and you'll see that right there, you're 2.48. If you're rotating around the 2 axis, meaning that you're in the 1-3 plane. If you're rotating around the 1 axis, you're in the 1-2 plane. So again, that's what we're looking at there. Okay, turns out the walls were not entirely frictionless. That's your full 3D plane. Entirely frictionless, and we have engineering shear strain in that 0.0018 in the 2-3 plane. Write out the new full 3D stress and strain tensors. Well, if I have engineering shear strain, I will have engineering shear stress. So that 2-3 will be in my epsilon 2-3 and my sigma 2-3, because we have that relationship that we developed previously. So I'm going to reevaluate epsilon 1, epsilon 2-2, all those good, all of our friends essentially that we're going to be bringing back here. So epsilon 2-3, not 1-2, should be 2-3. So epsilon 2-3 will be 0.0018. That's a typo there. It should be 2-3. And I'm going to solve because I know, actually I'm going to plug in my values, just to value in my material properties, because I know that this must be equal to 1 over y times 1 plus nu times sigma 2, 3. I don't know why I'm thinking it's sigma 1, 2, but again, you would just switch those notations with, instead of 1, 2, it'd be 2, 3. And then you could put those in basically your tensor. So sig 1, 2, again, sig 2, 3, very similar, vice versa. It's just we see I messed up that value looking and thinking up of a different problem. But the values would actually be the same thing there. All right, what rotation orthogonal basis test for the new would give me, for the new stress tensor, would give me my principal stresses. And actually we do strain. Let's show the strain there as well. Again, I'm thinking it's 1, 2, it's 2, 3, but again, go with me. Please forgive my mistake, but you can kind of work it out and then see how does your problem look like. So strain 1, matrix form, we got it. And what rotational orthogonal basis set, new coordinate vectors will give you principal stress state? What are the values? This can be done if you have the full 3D tensor via eigenvectors, eigenvalues. So eigenvalues, those are my principal stress values for this particular one that I've worked with. And eigenvectors, i.e. your new basis set, it's going to be given right here. So remember, these eigenvectors are your new orthogonal basis set. So you see here that because I'm basically have plane stress in the 1, 2, which in the 1, 3, I have my three direction remains unchanged. So I still have my 0, 0, 1 coordinate vector, but you see I have another new basis set essentially derived here. So that's very, very important. And you see in that stress tensor that I don't have, basically I have plane stress around there. So excellent. So I can now look at, and you could actually just create that. So there's lots of different ways you can solve this problem, but when you're asked for the new orthogonal basis set for principal stresses, eigenvectors, eigenvalues. And now on to the next problem. So now we can go on to, basically I'm looking at the next generation of wetsuit materials. Biomimetic autofer behaves similarly to a polymer. So if it's polymer, I know my Young's modulus, I know my nu. I am going to quit my kernel and clear everything because I don't want any crosstalk in between my variables. All right, so let's see what we've got here for this problem. So I measured the stresses and strains at different rotations. So we can kind of see here and write out some of the values that we know, and then we can kind of work through and look at our tensor initially. So we do have a stress in the 1, 1, the 2, 2, and the 1, 2 in our original coordinate system. And we actually know the values of sigma 1, 1 and sigma 1, 2, but we don't know what sigma 2, 2 is. So that's an unknown. Excellent. So let's go ahead and we don't know what 2, 2 is. That was a typo there. Then I rotate 36 degrees counterclockwise around the 3-axis, and I get some strain values here. So let's go ahead and take a peek at that. So we're given some of these values here. We know the rest of those stress values must be 0 because we're only looking at applying stress in the 1, 2 plane. So we can start to work through this problem. So y equals 1 times 10 to the 9. Nu is equal to 0.4. We can start defining some and setting up our tensor solve. So in my original sig OG, I do know my sig 1, 1. It's minus 55 times 10 to the 6 megapascals. I know that minus 47 times 10 to the 6, 0. And then I also know minus 47 times 10 to the 6, 47 times 10 to the 6. I don't know what sig 2, 2 is, but I can solve for that. And the rest of them are all 0, 0, 0. Excellent. So I've got my sig OG. I can also start to possibly think about what my strain OG is, but we could, again, let's go pull, let's give ourselves some room to work with here. And actually, exactly, let's move this over just so we can see what we're given. So my strain OG, I know that I will have a strain in the 1-1. Actually, we could, let's go ahead and let's start typing. We could try to start typing them out, or we can start to fill these here. And actually, we can define. Actually, I could set up my strain 1-1 OG equation. So I could actually solve it in. There's many ways you could kind of go about trying to solve this problem. But actually, I can go ahead and let's make this a little bit more general. So sig11 OG minus 55 times 10 to the 6, sig22 OG, we don't know. But I do know sig12 OG. So let's define that. Sig12 OG is here. So I can actually write out some of the equations. So I actually know what E12 OG is, just 1 over y times 1 plus nu times sig12 OG. So I could actually plug that in right now for my strain tensor. There should be a strain in the 1-1. So, and then there also should be a strain in the 2-2, and there will also be a strain in the 3-3 as well. So we could put, again, our strain OG tensor. So E11 OG, E12 OG, we already have that, 0, because there's no shear stresses, so we know that. E12 OG, E22 OG, 0 again, because there's no stress in the 2-2. We can also just plug that in, and we know the relationship. E11 OG is just going to be sig11 OG minus nu times sig22 OG plus sig33 OG. There's no thermal strain here, so we don't have to worry about that, thank goodness. So we can just put that there. We know sig33 OG is basically 0. Sig22 OG, we're just making sure everything is consistent. Sig33 OG. And now we have that expression here. We can plug that in. We also know E22 OG, we know E33 OG, and so we can start to define out. You could do this a lot simpler if you use your, basically your compliance tensor, but this is just one way you could solve this problem. It's kind of more similar to what we've done in class. It's a slow way, so again, I would definitely suggest perhaps doing it with your compliance tensor, but it's a nice way to just kind of think about the whole problem, given the information. We're given a significant amount of information to begin the problem. So sig11 OG, sig22 OG, here we go. Let's define them all, and not E33 OG. So we have, and we can actually see, we can get our whole original compliance tensor as long as we have sig22 OG. So we just need to solve that one. We can now start to define what's our new prime, basically our strain tensor. So we can actually go ahead and start to define that. And we're doing a rotation around the 3-axis, so I'm going to do R3. So we can actually start to define, and actually we could just rotate that tensor right now and keep, and actually you could kind of make sure some of them match, hopefully. So it's going to be E11 nu, E12 nu, or actually, here we go here, 0.173, because that's what we're given here. And I need to divide that by 2 because that is engineering shear strain, so make sure we do that. We should, again, as long as we rotate in 1-3, and actually we could do that right now as well. So we can rotate that sig OG tensor right now if we want to. So my sig nu is just going to be equal to, I can do R3, but we can also start to kind of plug in some of these other values. And actually, let's define this as a variable just to make sure, again, let's keep everything kind of consistent and on track. E33 nu is going to be equal to that value there, and then we could kind of plug those in when we need to, essentially at that point. Excellent. So before we can decide whether there is a strain in the 1-3, we need to basically rotate that stress tensor to see if there is a stress in the 1-3. So transpose here, theta goes to 36 degrees, and then we'll make that 36 type the degree positive because it's counterclockwise. We've got lots of, all right. So we can look at this and see that, and like we can look at the matrix form. Don't do math on the matrix form. Remember, you're not able to do that. But we see because we're rotating the 3 direction or around the 3 axis, we still see. Actually, we could look at this as well. We still don't have those stresses that aren't in the plane stress as we would anticipate. So if we know that there is no basically value here, and we can see basically that rotation and everything there. So we can now eliminate a lot of the new strains. Actually, we can actually, looking at this now, we have an equation here for our first stress, and we know basically what it was previously. So we can actually start to solve this problem. But again, we'll wait for just a second before we start to get it solved. Because, again, we can start to define that. You see sig13 in the new coordinate system 0, therefore we know this must be 0 as well, comma, we know that there will be, it's just the same thing, and we can just copy and paste that, E12 new, E12 new. There will likely be, most likely, almost absolutely, a new strain in the 2-2, and there will not be a strain in the 2-3 because of that 0 there. So 0, and then we can kind of continue 0 there, and then 0, 0, and then there will be most likely again a strain in the 3-3 because there seems to be some stresses elsewhere. Excellent. So we're seeing what we have to solve for. So we need to solve for E11 new, E22 new, and we need sig22, OG. That's what we need to solve for. So luckily, we can see that, and we know that our stress. So we have our EPS new. We could do actually our sig OG, matrix form. Again, apologies for that, but the computer went off. So we had to re-record this one, but we'll be okay. Sig new, matrix form, and EPS old, EPS original, OG, matrix form. So what do we have here? So we need to solve for our new values here. So we know that my new E12, we can solve that my new strain must be equal to 1 divided by y times my 1 plus new times my new sig12, which is right here. So we can do that times this, and then solve for sig22 OG. Once we do that, all right, we got this. And here we go here. Now we're starting to cook with gasoline. So now I could do my, and actually I should just reevaluate. Sig OG, boom. Sig new, good. EPS OG, good. All right, so now we're starting to look pretty nice. So we just need to solve for E11 new. Well, E11 new is just going to be equal to 1 divided by y times basically my sig new 1 minus new times sig new 2 plus plus sig new 3. That'll be my E11 new. And then I could do my E22 new will simply be 2211. Excellent. And we got it. Fantastic. So we're asked, excuse me for here. We are asked now to write out the stress tensor, strain tensor, original, rotated, fantastic. What rotation will give a 3D principal stress state? What are the values confirm the orthogonal basis set? Well, if I look at my sig OG, that's plane stress. So if I can find, we should think it should be a rotation in the 1-2 plane. It has to be actually. So we can do eigenvalues, sig OG. Excuse me. We can do eigen vectors of sig OG. And I could do my OG basis is equal to 1, 0, 0. Excuse me. 0, 0, or 0, 1, 0, and finally 0, 0, 1. So I can look at the angle, vector angle, between this one here and then also my OG basis. So, and then we need to multiply that 180 divided by pi. So we see that angle here. One of the weird things that Mathematica does is it will switch, basically for your OG basis for eigenvectors, this is kind of correlate to this value here. It's trying to kind of arrange it from largest value, so you may have to kind of play around in here to see the angle. But I could confirm that by just doing, if this is the angle here, I could also do, see that angle there. We're looking at different ones. So if I do transpose of R3, 3 dot sig OG dot R3, 3 here, you can do slash n, actually, excuse me, slash dot theta goes to 36 degree. So we can look at this matrix form. These values, actually not 36 degrees, excuse me. I'm thinking of my proof later on down the line. We do this, voila, look at eigenvector values here, here, 0, 0, excellent. We can do 36 degrees, and actually we could confirm sig OG, sig nu, matrix form. So actually you see the value right here. Excellent, looks good. But if you did, for example, basically R3 dot with 1, 0, 0 slash dot theta goes to 36 degree, you will find that new basis set as well. So if you had to write out, you would get that. And you could do kind of the same thing to figure out the angles here as well. So for example, if I did a rotation of my 100 to be this 11 degrees, I would find, look at it, boom, boom, you got it. If I did 010, you can have that as well. So you can try to sketch that out and see what those rotations are, but this is a nice way to kind of solve that problem. So now we can move on to the next problem, and problem 4. So now we can look at essentially the strain tensor for this problem for a ceramic material, and basically how we would rotate to get to our principal stress state. So let's go ahead and take a look at how we want to solve this problem here. So we could write out the full 3D stress tensor, and we want to write out a strain tensor for an additional 33 degrees clockwise rotation. So ceramic, 300 times 10 to the 9 gigapascals, Poisson's ratio equals 0.2, full 3D strain tensor as well for 33 degree clockwise rotation around the 2-axis, microstrains. So we can start to basically write out this problem. So let's keep that visible so we can look at it. And let's clear our kernel. And now we can start to get moving on this problem. So we can now start to, we can pull out these values, or we can, let's redefine it. So y is equal to 300 times 10 to the 9th. Nu is equal to 0.2. And we could evaluate that. Define our strain. The strain old. So 1v7 minus 18, 0. 27, 324, minus 37, 0, minus 37, 15. And we got it. Times 10 minus 6. Make sure that we're working with that there. Excellent. So 3D strain tensor. So we got the old strain for rotation counterclockwise around the 2-axis. So actually we'll look at the principal. So we could do eigenvectors. So those would be our new coordinates, or our new orthogonal basis set. Those would be your eigenvalues as well. Excellent. So that's a pretty quick, straightforward way to basically solve through those problems. Those are going to be, again, those eigenvalues for, again, your principal strain state. Now we need to write the tensor, got that. Now rotation 33 degrees counterclockwise around the 2-axis. So we could pull out our old R2, or we can start to kind of memorize that rotation matrix kind of notation. Could be very helpful. So I'm going to do transpose of R2 dot R strain old dot R2 slash dot theta is going to go to 33 degrees positive because it's counterclockwise. Excellent. And we got it. Fantastic. So those are those values. So we could also do, again, the stress data as well. So we can now, and this is where it would be very wise essentially to have set up your, basically your compliance tensor, excuse me. So one of the things we're going to have to do is we're going to have to translate this into a 1/6 basically column in order to work with this value, but we can pull that in and we could use this, and this will be very, very helpful for this particular problem where you're given strains and you're asked to actually grab the stresses. So for the old system, it's quite easy, and for the new one, it's not going to be too bad, although we're going to have to write those out. So I can just simply do, we know that our strain is equal to S dot our old stress. So, or actually, excuse me. So actually we can solve for, so we can get, or you could do the inverse, but we could kind of write it out like this. Our old stress, sigma 1, sigma 2, sig 2, 3, or sig 1, 3. It really doesn't matter as long as you're consistent, at least for isotropic, linear elastic isotropic materials. But let's take a quick peek at that. I believe that if you look back to lecture 6, or actually even, excuse me, lecture 5, we should be able to see it should be 1, 2, 3, 1, 3, 1, 2. Let's just be consistent. 2, 3, 1, 3, and then sig 1, 2. Excellent. So that's our old stress, our strain old. We can define that as well. So we can start to extract those values. So our strain old, we can put that into 1/6 as well. We can start to take a peek at these materials. So old strain is going to be strain old 1, 1, and then strain old 2, 2, strain old 3, 3. Again, strain old. You're getting the picture now. So 2, 3, strain old 1, 3, strain old 1, 2. And then now we're cooking. So now we can just go ahead and solve. So solve old strain set equal to, or strain old, actually should be old strain. Old strain, use better variables, set equal to S dot old stress. And then, voila, we got our values. So we can then take that and actually do a rotation to find your basically the stresses in the new coordinate system as well. So you can actually do that quite simply. But let's actually see make sure we're getting all of our problems put to bed. So we can see, and actually now we can go ahead and transpose R2 dot S dot R2. Oops, we can't do that because that is a 1/6 or 6/6, so we cannot rotate that and get that easily. We'll look at that in our anisotropic lecture, which is about to come. So we could actually just do this. I was trying to be a little bit lazy. Let's do this the good old-fashioned, the hard-working way, so that we can basically get these values here. So I can go ahead and define my old stress. We could put these values together here. I could do this a 1/6. Delete this. Delete this here. Move that. Or actually, we could do that in a 3/3. So let's plug that guy in there. Let's plug this one in here. Actually, excuse me. We'll do 1/6. Plug that one here. So we're just rearranging again, putting them in order 1/6, so we can do our. We can start to play around with some of these rotations and define our old stress. Then we can figure out our basically new strain, all the good stuff. So let's plug these in here. Let's plug this one in there, and there we go. So that's our old stress 1/6. So I could actually transpose that. Old strain, or old stress, excuse me. And then rotate it. But we need to make sure, and again, it's going to be, let's say 30, so 33 degrees. But remember, we're still in the same problem where we need to put it in the 3x3. So they're incompatible shapes. We're not reaching that value here, so we need to put that into a 3x3 now. So we can redefine that and make that work. So let's go ahead. Trying to think of a way if we could do this quickly, but instead, let's just go ahead. Let's do it the old-fashioned way. So I can do stress old, and I can pull out old stress, bracket 1, stress old, or old stress, the 6th value, old stress, which value would that be? The 5th value, yep. So now we can copy that. Let's click, oops. There, yeah, let's blow this up. Tired of looking at a small screen. We're not getting any additional information there. 6, 2, and then we'll have that as our 4th. Let's just make sure, yeah, that's our 4th value there. So we can put 4 here, we can put 6 there, and then we make sure that we put our 5 there. Excellent. There. Now we can do stress old, matrix form. Now we can just plug in instead of old stress. Stress old. Let's type in stress old. And voila. And we can look at this in matrix form. And that would be our rotation. Fantastic. Excellent. Problem 4 is done. Let's get into 5. So I have a Pepsi can, 5 inches tall, 2.2 inches in diameter, thickness of 0.01 centimeters. So Pepsi can, metal, aluminum, exactly. And it tells us we could withstand a certain amount of strain. Let's clear our kernel here, and then let's quit that. So our Young's modulus, or let's do our radius. Our radius is equal to, which one is it? So 2.2 divided by 2 times 0.0254. Thickness, 0.01 times 10 minus 2. And R over T, make that better be equal, greater than or equal to 10. Excellent. What else do we have here? Aluminum, failure can only extend here. So let's write out the sig H is del P times R over T. Sig L is equal to sig H divided by 2. EH is going to be equal to, we can define that here. EH is going to be equal to 1 over Y. So we can define Y is equal to 100 times 10 to the 9th. Our nu is equal to 0.3. So 1 over Y times sig H minus nu sig L. EL is equal to 1 over Y sig H, or sig L, excuse me, minus nu sig H. And now I can go ahead and start to solve. It could extend approximately 12% before failure, so 0.12 is equal to EH. It's got our del P. So our del P is equal to this. What's our sig H? What's our sig L? What's our EH? What's our EL? Got him. So we are in the principal stress state. So we got that pressure, stress tensor, we got that. Where is the shear stress maximized? That it'll just be sigma 1 minus sigma 3. So sigma 1 is delta H, or sigma H, excuse me. Basically minus 0 over 2. So your maximum shear stress for any thin wall pressure vessel is always going to be basically your sig L. So divided by 2. 0, so sig L. Excellent. Is my fracture pattern correct? Yep. Basically, if I look at my hoop stress, it's always going to pull around that circumference, and then it'll fracture like that. Excellent. Last problem. So I have a polymer, polycarbonate, primarily bonded through intermolecular van der Waals interactions model with the Leonard-Jones potential with those parameters here. So now, and we're told polycarbonate, we need to look up and see what is that TG value. So we see, actually you could look at, our TG is going to be, let's go ahead and look. Let's look at it varies wildly. And again, that's true for many polymers. So let's go ahead and let's see here. But let's just say last transit temperature 147. That looks pretty good, pretty consistent. So 147 is our TG. So below TG, we need to do what? NT greater than TG. So below TG, I'm going to treat it exactly. Above TG is just going to be that. For below TG, I need to use my good old friend potentials and solve it. So let's go ahead. Let's clear everything here. So let's define our Boltzmann's constant times 10 to the minus 23. So we have that. Our n sub x is 10 to the 27. So we got that. And then we know that our temperature, we can actually plot and see how it looks like. So our Young's modulus plot is nx times k times t. And then plot from t from 147, or a little bit above it, to 150. And you see the value. It's about 2 megapascals, so it's a very, it's not a very, it's a somewhat of a flexible polymer there. So now we need to plot it for the temperatures below. So now I could take epsilon, plug it in, so 1.5 kT, so K times temperature. Again, we could assume room temperature. Again, that value will change slightly, so we could keep that T in there, but when you usually give, is basically that value at room temperature. So it's not really changing effectively, so we could essentially give it that value. So now solve for dLj as a function of r, set it equal to 0. Let's give our, because we need to find our r naught. So now that I have my r naught, I could take the derivative and actually look at that value. So we don't know the number, because it's a polymer, we don't know the number of nearest neighbors, so we're going to use basically our function that is just going to be 1 over r naught times that value. So we just use 1 over r naught, and then we can kind of see here derivative ULJ with respect to r to evaluate it at r equals r naught. And you see about 10 gigapascal. So quite a large difference when it's below TG, above TG, rubbery polymer versus other polymer. So we are finally done. So study hard, do well in the exam, and I'll see you all in the next video. Thanks. Bye.